Okay, welcome everyone to the 69th meeting of New Directions in Group Theory and Triangulated Categories. Today, we are very pleased to have Amnon Yekutieli from Ben-Gurion University as our speaker, and he will be talking to us about a DG approach to the cotangent complex.
Okay, thanks. Thanks, Rodrigo, for the invitation. Let me say a couple of words before I start. First, the slide, well, that's too late. Slides are available. You could have downloaded them and you can download afterwards. One thing about questions, don't wait. Please, if you have a question or a remark, stop me in real time, preferably by doing something like this or by voice, because I can't see, I can't follow the chat. So if something's not clear, be sure to ask. Okay, so let me start the introduction about this business of cotangent complexes in a possibly unusual point in history, which is the work of Grothendieck. So in EGA4, towards the end, Grothendieck discusses square zero extensions of rings. I think this is probably where one should start, although at the time, of course, there were no cotangent complexes. So let me say a few words on that. And throughout the introduction and throughout, I guess, the whole talk, everything is going to be commutative. So consider a ring A and a surjection of A rings, P from E to B, which with the property that the kernel of this surjection is square zero. This is what's called the square zero extension of B by N. And one can easily see that N is actually a B module because of this property. So this is the situation that Grothendieck considered, and he gave a name or notation for the set of isomorphism classes of these extensions, XLCOM, and it turns out to have actually a canonical B module structure. So Grothendieck understood in the sense of having not so long exact sequences, but the beginnings of the long exact sequence of cohomology, that this functor is a sort of a first right-derived functor of the functor of derivations. So the reference for this in EGA. But somehow Grothendieck was stuck. His homological algebra was suited for abelian categories, for linear functors, and not for this nonlinear situation. So he really couldn't proceed any further, at least in EGA. But shortly afterwards, maybe, well, I don't know, a few years after EGA4 was published, simultaneously, I believe, André and Quillen made a breakthrough in this direction. And this was using simplicial methods. Let me use the code word pair of rings, for homomorphism, because all this business of extension and differential forms really pertains to pairs. So using simplicial polynomial resolutions, so resolving B by a simplicial polynomial resolution over A, Quillen and André constructed the cotangent complex. This is a well-defined object in the derived category of B modules, in the sense that it's independent of the resolutions. So this is an algebraic setting, and shortly afterwards, Iluzzi extended this to algebraic geometry, also using the simplicial methods. So this is 1960s, and suitably interpreted, it's not so easy to see how, this cotangent complex is a total left-derived functor of the functor of differential forms. I'll get to explanations later, and in particular, in zeroth cohomology, it recovers that, as would be the case of a left-derived functor of a right exact functor in the classical situation. So relating this cotangent complex to Grothendieck's work, the H0, well, the X0, for an arbitrary module n, the X0 recovers the derivations, and more interestingly, the group of extensions of B by the module n is canonically isomorphic to X1 from this complex into a variable module n. And this result is probably the crowning theorem of Ilouzi's book. It was already figured out in the ring case by Quillen. So this is history. Since then, so I think 50 years have passed, cotangent complexes have become more and more important and more and more complicated, especially in derived algebraic geometry, where they got new roles, and on the other hand, there are all kinds of variations. And all this is, let's say, nice and well, except that nobody knows really what they look like. So if you're in some abstract homotopical context, there is no resolution giving this cotangent complex, as far as I know, except in characteristic 0, where things are sort of too nice. In fact, normally the way people in homotopy theory and derived algebraic geometry define the cotangent complex is by what I would call reverse engineering these formulas. So perhaps this is the best one. The cotangent complex solves the functorial equation. It represents a derived version of this functor. So they go like this. Attacking it concretely doesn't seem to be possible. So what I want to do today is to try something new, namely to give a rather explicit construction of the cotangent complex using differential graded rings. I give it a different name. I will call it the left-derived cotangent DG module. One of the reasons is because I can't really prove yet that it coincides with the original one. So there will be conjectures about that. I will prove that it has many good properties, which are evidence, but I can't really prove them. I'll explain.
Are you in characteristic 0?
No. I am not assuming any arithmetic restriction. So that's the big thing. So no arithmetic restriction whatsoever, and using differential graded methods only. In fact, commutative differential graded methods only in the statements. Under this setting, I believe that what I'm saying is totally new. At least I haven't seen anything resembling it in general. Again, without arithmetic restrictions. And furthermore, it works, we don't need to work with rings. We can replace A and B by commutative differential graded rings. So I'll explain all these concepts and the constructions, and I'll say some of the important properties. I was hoping to be able to actually give some proofs, but there's no time for proofs. Things will be on the archive quite soon. Some of them already are. So there will be several conjectures, though, which could be interesting for people. To end the introduction, let me thank two people who helped me understand these things. Luc Ilouzi, who was one of the earlier people I mentioned, and my nephew, Amnon Yekutieli, who knows the homotopical picture, and also a couple of my colleagues who gave comments on an earlier version of this talk. Okay, so I mentioned all kinds of things: differential graded rings, semi-free, cotangent. So let me briefly explain what I mean. And in fact, what I'm saying is not very much removed from what you have from the derived categories of Grothendieck and Verdier, with a little bit of extra technical stuff added, but nothing dramatic. So I'm going to use the word differential graded ring. It's kind of an oddity instead of differential graded algebra. There's some good reasons for it, but anyhow. So a differential graded ring is just a graded ring with a differential And the interaction is the graded Leibniz rule between the differential and the multiplication. And I will be interested in very special kind of differential graded rings. They're all non-positive. So in the homotopical world, where people use lower indices, they will be non-negative, and sometimes it's called connective. It's not quite the same as connective, but very close to it. I will insist on strong commutativity. Strong commutativity combines two properties. First, there is the Koszul sign rule, this plus or minus sign, depending on degrees. And the second condition is that odd elements all have square zero. And this is essential for the story. A commutative differential graded ring is a differential graded ring which is both non-positive and strongly commutative. I'll use this abbreviation. So these are the objects I'm studying. Of course, commutative rings are seen as CDG rings concentrated in degree zero. So the idea is we initially want to study commutative rings. Commutative rings, well, you need to do something in order to make derived constructions. So we pass to this commutative to these CDG rings. And then we say, actually, these CDG rings are so nice, maybe we can study them on their own. And so we're doing that. Some technical words. So if I have a fixed CDG ring, I can talk about CDGA rings, which are which are rings B equipped with a structural homomorphism from A to B. And notice that in this situation, the differential of B is usually not alinear. That's one reason why I don't say algebra. So B isn't a DGA algebra, it's a DGA ring. The differential is not alinear, it is only A0 linear. So these things are quite delicate, only A0 linear. Now I quickly want to explain what the semi-free business is. So a standard gadget is if you have a CDG ring and you forget the differential, the graded ring is denoted by this natural symbol. The second thing I want to introduce is, given a graded set, just a set of variables with degrees, one can make the commutative graded polynomial ring over the integers, and you just make the polynomial ring, and you're adding and you're imposing the Koszul sign rule, and all odd degree variables have to square zero. So this is kind of the free object in this commutative graded world. Using this concept, I can say what is a semi-free differential graded ring. So over A, so a differential graded ring B is called semi-free if, after forgetting the differential, B becomes isomorphic as a graded ring to a commutative polynomial ring over A. So it's rather simple. Notice that this definition only works in the non-positive setting, in which I am, so things are less complicated than in general. So this is what it means to be semi-free, and these will be the things we'll work with. So all resolutions I will ever do in this lecture will involve such semi-free resolutions, nothing more complicated than that. I'll give examples as well. So what's a resolution? If I have a B, which is an A ring, so the input is this, a semi-free resolution is I stick in the middle some B tilde, where B tilde looks like that, and I insist that this homomorphism is not only a quasi-isomorphism, but actually surjective. This is very important. And these resolutions always exist. Here's an easy example. I'm not sure if I have time for these examples or not. Let me check my time for a second. I think I can quickly give the Koszul examples. So the easiest example and the nicest example of a semi-free resolution is the Koszul complex. So suppose the ring A is the integers and the ring B is Z mod 6. So we have actually a pair of rings. And I want to find a very easy semi-free CDG resolution of B, and this turns out to be the Koszul complex of the number 6. So as a differential graded, well, as a graded ring, it's the polynomial ring over the integers with a variable x in degree -1. So by our rules, x squared equals zero. So really, we just have 1 and x. The differential, so we have this, and that we declare the differential of x to be 6. And it's easy to check that it's a differential weighted ring, a CDG ring. And writing things additively, we have b0 here, b tilde 0, b tilde -1. This is the differential sending little x to 6. And there's no kernel here, and the kernel is z mod 6. So you see, these CDG resolutions are sometimes just Koszul complex that we are, familiar with from forever, although it's actually a very rare situation. So this only happens when B is what's called a Koszul regular surjection. So it means the kernel is generated by a certain Koszul regular sequence, which could be infinite, by the way. That doesn't matter. Finiteness plays no role in this game, but it means the Koszul complex is acyclic. But in general, one can't avoid throwing in infinitely many variables, infinitely many degrees. So the Koszul situation is misleadingly nice. But it's good to have an example. Anyhow, so these semi-free DG rings have a lifting property. So suppose fixing A. Yes, I'm fixing A. Did I say that? Well. Yes, CDG. So I'm fixing A and I'm looking at all kinds of CDGA rings. So suppose this is an arbitrary homomorphism, and I would like to resolve it and to have a lifting. So I already said that resolutions exist, namely I can find this vertical arrow, which is a surjective quasi-isomorphism from some polynomial b tilde. I can find this surjective quasi-isomorphism for b tilde prime. Again, many choices, but the thing is, it's always possible to lift G to a homomorphism G tilde. So these liftings always exist. Of course, the problem is there are too many of them, and that's where the game begins to be more complicated. Let me quickly, just before I move on, I will need the concept of semi-free DG modules. So everybody knows what DG modules are, I guess. They form a category, well, like the category of complexes over a ring, but there are no modules, just DG modules. And just the same way as complexes, we can invert quasi-isomorphisms and get the derived category. And among the DG modules, well, I'm only interested in bounded above DG modules. In this case, it's very easy to define what it means semi-free. Like in the case of rings, a DG module is semi-free if after forgetting the differential, it's a free graded module over the associated graded ring. So in this at least unbounded or non-positive game, to be semi-free just means that after you forget the differential, you're a polynomial ring or you're a free module over a free graded module. So it's quite easy. Okay, so this is all I need to say about this DG algebra. If you want to read more, it's actually in my book on derived category. There's a big discussion of that. Now, I said already before that we're interested in pairs, namely the extensions of B. I mean the differential forms, the cotangent complex. It always depends on A goes to B. So we need a little bit of formalism for pairs, but it's really just a formalism. So I'm going to go over it quickly. So a pair just means a homomorphism from A to B. So the thing is, I want not only to change B, I want also to change the base ring A at the same time. So B and A have to move together to have an interesting theory. So that's why we work with pairs instead of with single modules. So B over A just means A goes to B. There's a concept of morphism of pairs. A morphism of pairs is just a commutative diagram. Namely, you go from this pair to this pair by these pairs of homomorphisms. So people who are expert in category theory will realize that this is just the arrow category of CDG rings. Now, likewise, one can have a semi-free resolution of a pair, but it's kind of cheating or overbuilding. So if I have a pair B over A, what's the resolution over it? So I write B tilde over A, but really the only salient contribution is just B tilde resolving B. So resolutions of pairs are just really resolutions of the second guy. But it's necessary to have this terminology. Likewise for liftings, maybe I'll draw the picture. So suppose I have a pair B over A, a pair B prime over A prime, and a homomorphism G over F. So there could be horrible, no conditions. However, I want to resolve them because I want to derive things afterwards. So I can resolve the first pair, which really means resolving B. I can resolve the second pair, which really means resolving B prime. And then I can lift the resolutions, which really means the G tilde that lifts the G. So it's really repeating what I did before. And since liftings of G exist, then lifting of this also exists. So that's the yoga of pairs. Okay, so now for something more interesting. By the way, are there questions so far? Or, I mean, am I going fine, clear? Don't tell me I'm going too slow. Okay, so I'll continue then. So this business of derivations now is, I'm not sure how familiar it is. I couldn't find good reference. I mean, I'm sure Boris Tsigan has known this probably 30 or more years ago, but I'll explain it anyhow because it's not so well known and I had to understand it for myself. So this is derivations in the DG world, in the commutative DG world. So let me try to explain here. So again, the input will be a pair of CDG rings. So what I want to generalize, maybe I should say, what I want to generalize is if I have a pair of rings, I assign to it the B module omega 1. So this is the classical thing. So if I have a pair of rings, I have the omega 1, the differential 1 forms, also known as scalar differentials. And we know from EGA initially, I guess, or from all kinds of textbooks, that omega 1 is a functor of the pair B over A. So we want to do something like this, but when B over A is a pair of CDG rings. And the answer is, it's almost the same. So, but I have to say, what are derivations, right? We know that this classifies derivations. And so we have to say what are derivations in the DG world. And so first, and we have to worry about degrees and so on. So a homogeneous derivation of degree I into a DG B module N is a homomorphism. Let's use the letter delta. You see, D is already occupied. It's the internal differential of the DG rings and the DG modules. So the derivations will be denoted by delta. So as to create less confusion. So a derivation delta of degree I, it means a degree I homomorphism for B to N, which is A linear, but regarding B, it satisfies the graded Leibniz rule. And then an arbitrary derivation is a sum of homogeneous derivations, and all these derivations together form actually a differential graded A module, which we denote by dir B over A. And among these derivations, we like the best the strict derivations, which are those that have degree 0 and respect the differentials. In other words, the strict derivations are the 0 cocycles inside here. Now, it turns out that as the classical thing classifies derivations, there's a similar gadget that classifies these differential graded derivations, and let me call it the cotangent DG module, just to introduce different notation. So it's a differential graded B module. So I didn't say that it's a DGB module. And it comes equipped with a universal derivation, which is a strict derivation. And this derivation, just like in the classical sense, induces an isomorphism of differential graded A modules between the DG module of derivations and this home from the DG module cotangent to the variable DGB module N. If somebody's interested, yeah, okay. So the construction is very similar to the commutative case. The properties are similar. There's a similar functoriality in terms of pairs. And again, generalizing the commutative setting. So we know that if B is a polynomial ring, then this guy is free. And in the DG world, it's very similar. If B tilde is semi-free, a semi-free CDG ring with semi-basis X, then this cotangent DG module is semi-free with basis the differentials of the variables. Or more plainly, forgetting the differentials, if B is a graded polynomial ring over A in the strongly commutative sense, then its cotangent module is a free graded B tilde module. And the differentials of the dx's are just, they commute with the differentials of the x's. So that's the structural theorem. Okay, so now that we have this cotangent DG module, I can try to play a game with it. So remember, what I want to do is to concoct some kind of a DG construction which will have the same properties of the cotangent complex in the classical world for a pair of rings, or in other words, for a pair of rings, it should recover the original one. But I just want to use differential graded constructions and to be as concrete as possible. And so here's how it goes. So first, as usual, to make a good definition, to make a sensible definition, you have to do something, and that's something. If it depends on choices, you've got to say in what way these choices are unimportant. And this is the homotopy theorem. The homotopy theorem, which is proved in a kind of auxiliary paper, which will be in the archive in a few days, I hope, says the following. So it's a kind of a complicated statement, so let me devote some time to the statement itself. So we're interested. So the input is a homomorphism of pairs of CDG rings, right, from B over A to B prime over A prime. So our tool is liftings, is resolutions. So we have resolved B by B tilde, we have resolved B prime by B tilde prime, but now somebody tries to trick us and they give us two possible liftings. They give us a lifting G tilde 0 and a lifting G tilde 1 of G. And we have to understand what's going on. And the problem translated to what we want to do is the following problem. Associated to B tilde, we have its cotangent DG module, which some semi-free DG module, probably very large. For B tilde prime, we have the same sort of thing. And the functoriality of the construction gives us a homomorphism from here to here. Now, we want to get DGB modules going to DGB prime modules. So we tensor here over B, well, with B over B tilde, and we tensor here with B prime over B tilde prime. But we have to be careful because The way B tilde goes to B tilde prime, and this is hidden in the construction of the homomorphism of tensor products. There are two different ways that it goes. It goes by G tilde 0 and it goes by G tilde 1. So we have to be careful and to remember that there are two distinct homomorphisms already on this level because of the I 0 or 1. And then, well, here, there's no choice. So we have two homomorphisms of differential graded B modules, and the assertion is that these homomorphisms are homotopic in the most common sense, namely there's a degree -1 homomorphism from here to here. Sorry, I should write like this: a degree of -1 homomorphism whose commutator with the differentials recovers the difference between the 0 and the 1. So this is the most, maybe the only difficult result in this game, and it's proved using, actually, so I have to say, it's proved using non-commutative methods. It might be possible to prove it otherwise, but I was not able to find any proof that does not resort to the non-commutative realm. So roughly speaking, the idea is to take this concept of cotangent DG module and extrapolate it to allow it to have sense also when the DG ring B is non-commutative. And it's possible to do that. It's kind of subtle, but it's functorial. And then we used what's called non-commutative semi-free resolutions, which have very good lifting properties and homotopy properties, and we let them play against the commutative ones, and this extrapolation, and make some calculations and prove this result. So the result here is completely commutative, but the only proof that I know requires a non-commutative calculation, which is not the first time that I've seen this. It seems to be kind of a useful trick. Anyhow, this is, I think, the only difficult result. The other results that I'll present are, in a sense, kind of sort of almost obvious consequences of that one, namely you do various yogas from derived algebra to deduce them. So the first one is this existence theorem, which goes like this. So I'm trying to mimic the cotangent complex. So I'm trying to construct some DGB module, and I'm using the word left-derived cotangent DG module because, well, it's the left-derived thing of what I introduced before, plus I don't really know that, I'm quite sure that it is, but I haven't proved it, so it's a conjecture, that it coincides with the classical thing when B over A are rings. So just to be careful, let's give it a different name for now. Also, the input here is a pair of CDG rings, so it's more general. So the assertion is that there is an object here which comes equipped with a canonical isomorphism to any construct that I will make using a resolution. Namely, for every semi-free commutative resolution B tilde, I have this guy, and it's canonically isomorphic to this one, which of course means that I need to produce a collection of isomorphisms between various incarnations of this, and to show that they're independent, but that comes, as I mentioned before, rather easily from this homotopy result. In fact, I guess many people can just imagine how such a proof would go. So it's unique up to unique isomorphism in the derived category, and it's functorial in the pair. And furthermore, and this is a good indication that it should be a left-derived functor, it admits a functorial morphism to the underived thing. And I forgot to say here, and also, if I apply H0, it's an isomorphism. So it's a non-degenerate thing. right? So it's not just a factorial morphism. In fact, it's an isomorphism on H0. So of course, when B and A are rings, it's just omega 1 B over A. But when B and A are DG rings, the cotangent thing is a DG module. And so we have to look at it H0. So that's the first result. But I still don't know that, yeah, so I'll mention these conjectures. Let's see if I have enough time to do the, well, I can quickly do the easy example from before. So remember, the easiest case of a semi-free resolution was the Koszul regular case. So Z mod 6 resolved by its Koszul complex. So the B tilde was this polynomial ring in this odd variable x, so x squared is 0, and the differential was d of x equals 6. Now, by the theorem that I gave before, this guy is a semi-free DG module where the bases are the de Rham differentials of the variables. But there's only one variable, this little x. And when I tensor it with B, it just becomes a semi-free thing over B. And so, in fact, it's a free, as a complex, it's a copy of B times this formal generator in degree -1. In other words, the left cotangent DG module is just B shifted 1, which agrees, I mean, this is all evidence, agrees with the classical situation. So this is the first indication that things are not completely ridiculous. And again, this is true whenever we have a Koszul regular surjection from A to B. So that's the first property. Right. But now let me say a few more properties, and some of them, and I'll mention the similarity and the difference between the properties of my gadget as compared to the classical cotangent complex of André Quillen and Ilouzi. And sometimes I can do more, sometimes I can do less. We'll see as the case goes. So I have to say that in my discussion, there's no finiteness whatsoever. Whereas in the discussion here, there is some finite presentation assumptions hidden, which I don't think are necessary, but I don't know how to remove them in all cases. So anyhow, for me, there's no finiteness whatsoever, and also no arithmetic condition whatsoever. So everything is over the integers. So the first classical thing, well, which is known for a pair of rings, is the transitivity triangle, which I think would mimic what is called the first or the second fundamental exact sequence in commutative algebra. But in our case, it goes like this. So we now have three differential graded rings. There's an A, a B, and a C. And of course, using the terminology, it's got to be a triple. So to a triple, we have a distinguished triangle. A distinguished triangle in the category of differential graded C modules, and it goes like this. So from here to here, it's just a functoriality of the L-cot. Likewise, from here to here, it's the functoriality. So these arrows are clear. And here we do a base change just in order to live inside here. So that's nothing. The point is, or the interesting fact, is that there's a connecting morphism such that the whole thing is, the whole thing together is a distinguished triangle in the derived category of C modules. And moreover, in a rather obvious way, this connecting morphism is functorial in the triple. So this is nice, and this is again good evidence because for a pair of rings, it's been proven by Quillen, by Ilouzi, and you can also find it in the discussion in the Stacks project. So there's another evidence. Of course, this is a bit more general because here we have differential graded rings. Now, the theorem I will state now has no classical counterpart because for rings, there's no quasi-isomorphism. It's either an isomorphism or not an isomorphism. For differential graded rings, we have quasi-isomorphisms. And here there's a surprise which is deeply connected to my erroneous lectures a year ago that were mentioned with Woodradi before we started the session. So something happens. I conjecture that there's actually a fracture, I mean, a dichotomy, but this has yet to be discussed. So I'll only mention one aspect of this potential dichotomy as a conjecture on the next slide. So suppose we have a quasi-isomorphism differential graded rings from A to B. Okay, so this happens a lot in the DG world. And I need to state what I want to state, I need to make one or two assumptions, which may sound weird. The first, so I assume either of them holds. The first is that U is surjective. So this, just set theoretically, is surjective. That's the first condition. The alternative condition involves divided power structures, which are not so popular these days. Kind of they faded out of popularity. Maybe some number theorists, maybe some homotopy theorists still remember them. So if the differential graded ring B admits a divided power structure, you can read these references. I just learned this over the last year or a few months, so I'm new to this. But if the target B admits a divided power structure, then the cotangent DG module of B over A is 0. So it's not, as far as I can tell, having a quasi-isomorphism is not, well, at least in this theorem, is not sufficient. You need to have a little bit more. And in the divided power case, it's kind of upgrading an old trick that I found in the literature. Now, what happens if A to B is not surjective? Or when it happens? So first of all, let's indicate in characteristic 0, somehow the whole story is so much easier than one might say that it's almost trivial. Nothing funny happens in characteristic 0. Remember, in the beginning also I mentioned that people know how to do DG constructions of the cotangent complex in characteristic 0. One thing that is, I think, deeply connected to this stuff is that if B is in characteristic 0, but what does it mean characteristic? It means that B0 contains Q, then B admits a divided power structure. So if we were in characteristic 0, this is automatic and nothing funny happens. However, and this is a conjecture which I came to, let's say, to consider as not completely fantastic only recently, is it's quite possible that if A to B is not surjective and B does not admit a divided power structure, and it's very easy to construct B's without divided power structures over the integers or in positive characteristic, even over the integers, if these conditions don't hold, I think there should be a quasi-isomorphism for which the cotangent DG module is not 0. So I don't know. It's weird. I have a strong hunch it's true, but I have no idea how to handle it. And I suppose that either finding a counterexample or disproving it will probably require homotopical or topological methods that are much more complicated than what I can do. You have a question, Deep? Oh, okay. So this is the first conjecture, and I don't have the appropriate methods to handle it. Let me say a few things about commutative rings. So first, let me remind you, Grothendieck's a B module of extensions, square zero extensions of the ring. So here we're rings. A is a ring, B is an A ring, and we're looking for square zero extensions of B by N, and this XL-com. And this theorem says that this XL-com is canonically isomorphic to the following thing. So you take this left-derived cotangent complex and you perform X1, namely H1 of our home, and they're canonically isomorphic as B modules. So it's actually quite easy to prove this theorem. The reason it's interesting is that it's another evidence. I mentioned this before already. This is Iluzzi's main theorem in his book, and also proved by Quillen in the case of the classical construction. And here it holds also in the new construction. So we have more evidence. The next thing I want to say is about the relation between this cotangent thing and formal smoothness. So let me remind you about formal smoothness. So I'm copying everything from EGA, but this is already in Matsumoto, also in Matsumoto and other texts. So we have a homomorphism of rings A to B, and we say that B is formally smooth over A if the following lifting property is solvable. So here's our pair A over B. Here's a variable square zero extension, and we have some input G. And the problem is, can we find a G tilde lifting G? If we can always find it, then this is called formally smooth. And if G tilde is unique, then this is called formally étale. So this is just from EGA4. And let me just say, because I'll mention it as the relation to smooth and étale is that they occur when A to B is finitely presented. So being smooth is just being finitely presented and formally smooth. And likewise for étale. Okay, so there is a reason why I'm saying all of that. So I can prove the following theorem. For a pair of rings B over A, the following conditions are equivalent. So let me first consider the first clause. So B is formally smooth over A is equivalent to the following two things. First, the left-derived cotangent complex, the cohomology vanishes in degree -1. And second, the cohomology in degree 0, which I remind you is always isomorphic to omega-1 B over A, these are rings, is a projective B module. So that's the first result, and the étale variation is only this little variation here. Again, the proof is kind of a nice game to play, like an exercise in diagram chasing. What do I want to stress? I want to stress that in the classical texts in Quillen and Iluzzi, they consider the situation where A to B is finitely presented, which means, so finitely presented, it means that the word formally is dropped. And what they proved is a little bit more. So they assumed finiteness, which is unnecessary for my theorem, but they proved more because the local structure of smooth maps and what's called standard étale or standard smooth morphisms, they proved that if this is smooth, then this cohomology vanishes in all negative degrees, whereas I only discuss a degree -1. Now, as they use some geometrical, some kind of commutative algebra properties, I have a feeling that these are not really necessary. So I allow myself to make the conjecture that this vanishing holds even without any finiteness. I haven't tried to prove it. I don't know how difficult it is, but I have a strong feeling that it should be true, just because in -1 it's true here, and in the finite presentation type, it's true there. And okay, so I'm at the last slide, so it looks like I'm almost on time. So I want to kind of, as a dessert, state two conjectures and a remark. The first conjecture is, I already said this before several times, is, okay, so I've constructed this left cotangent DG module. And what happens if I start with rings? Do I recover the classical thing or not? So there's a lot of positive evidence, but I wasn't able to prove it. So it might just be that I wasn't thinking clearly enough, and that it's not very difficult, or it might require strong technology. I have no idea. I have a feeling that I just wasn't clever enough, but I don't know. So this is the first conjecture, and it's most likely true. The second one is vague, especially vague because I'm not very illuminated. I barely know anything about modern homotopical algebra. So I do know that in various flavors of derived algebraic geometry, or more recently spectral algebraic geometry, there is a cotangent complex. I think, in fact, in Lurie's work, there are at least two different kinds of cotangent complexes. So and they're defined completely different. They're defined, as I said, by co-representing certain kinds of functors, which are stated in terms of various homotopical localizations. So vaguely speaking, I would like that under certain conditions, so if let's say the commutative differential gauge rings that I have can be interpreted as certain rather degenerate, let's say, spectral rings, and then hopefully, if one specializes Lurie's construction and downgrades it to the algebraic level, that there should be an isomorphism like that. But this is completely vague, and I have no idea whether such a comparison holds or not. I really don't know. And the last thing is actually on a positive note, which is something that might be completely new or not. I don't know, because I haven't seen it in the literature, except in EGA4, but nothing since then. Remember I talked about certain cotangent constructions for non-commutative rings. So it's possible to, given the input, so if B over A is what I call a central but non-commutative pair. So A is commutative, B is a non-commutative differential graded ring, and A to B is central. For example, B is a ring, and it's an A algebra in the classical sense. One can make a slight modification of this construction and obtain some kind of complex of DGB bimodules. And let's call it informal. I mean, I haven't typed it yet, but calculations say that this non-commutative version calculates, at least for the case of rings, what Grothendieck referred to as X without al, X al without com. So it calculates. So E to B is a surjection of non-commutative A rings with square zero kernel, and it calculates the isomorphism classes. And I think that this non-commutative variant does that. Certain examples include deformation quantization of Poisson brackets and so on. So I should really end. I'm really over time now. So that's the end.
Thank you, Amnon. Let's all unmute ourselves and give the speaker a round of applause now. Okay, if you have any questions for Amnon, you can ask them now.
So this last bit that you are talking about, then that would be related to partial homology?
This?
The non-commutative case?
Yes, definitely. I mean, well, at least when B is commutative and you're looking for square zero non-commutative extensions, then these are exactly star products or quantizations. Yeah, so it's Hochschild. And I guess in general, I haven't studied it, but yes, it should be. Also, Grothendieck already talks about this in EGA. For example, when A is a field, so you need the extension to be split additively, and then you get a Hochschild extension. And I think that's exactly that. So those extensions, which are split as A modules, are the Hochschild H2 Hochschild cohomology So that's another way of calculating it. But this is not using a Hochschild complex. It's an arbitrary semi-free resolution, which so yeah. But it's very yeah. So it's slightly more general than Hochschild theory. Yes.
Thank you, Maria. Any other questions?
So may I ask,
boss.
I'm kind of always a little bit somehow in my head, commutative NDG is a little bit, you know, is perfectly okay in zero characteristic.
Yeah, it has a bad reputation. It has a bad reputation over the integers.
Okay, yeah.
Yes. Yes,
I
that's
mean,
true.
yeah.
It has a bad reputation, but I think I can save its reputation.
Yeah, that's great. Okay.
But the thing is, and this is exactly what, so when I gave this lecture last month, Iluzi was in the audience and he was disturbed by this exact bad reputation in characteristic, in arithmetic settings. And the thing is, perhaps the key word is I do not use Quillen model structures at all. So it is, so we know that these CDG rings in character, well, over the integers or in characteristic P do not have a good Quillen model structure, but I don't use Quillen model structure whatsoever. I use, if you want, manual hard labor techniques, resolutions, which are completely independent of Quillen. And this dichotomy that I mentioned about the non-zero, which was it? This conjecture, this actually, I claim, I'm going to write this down, that over the integers, the standard localization of CDGA or CDG rings by inverting all quasi-isomorphisms is actually the wrong thing to do. And the anomaly is there because you're doing the wrong thing. So what's called homotopy of CDGA, or I call it the wild derived category of CDG rings, inverting all quasi-isomorphisms is not the proper or not the beneficial thing to do. And I propose that one should only invert the surjective quasi-isomorphisms, which gives you something completely different, very manageable, has a good right calculus of fractions, not left calculus of fractions, which probably means there is no Quillen model structure in play, and yet a very good category. The distinction between these two categories is somehow captured by the possibilities of non-surjective quasi-isomorphisms and without divided power structures having non-zero cotangent complex. Of course, in characteristic zero, everything disappears because, well, one way of saying it is because of the omnipresence or omnipresence of divided power structures. So it is particular to non-characteristic, away from characteristic zero. And there, I think, I mean, I'm allowing myself to conjecture, it's kind of bold, that things are different than what was traditionally expected. They will never be well with Quillen's theory, but there's a good theory if you only invert surjective quasi-isomorphism. I call it the tame derived category. And they're not equivalent. So again, there's a conjecture that you get different categories and the wild one, which is the wrong one, is really bigger or different from the original one. But and again, studying this and making sense and checking correctness or counterexamples would probably require higher methods than I have, namely topological or E-infinity methods to examine this. So I'm raising questions which I probably am not able to actually answer myself. But Boris, they have a bad reputation, but I think this reputation is ill-gotten. It was kind of, they were kind of, how should I say, their rights were being repressed or something. I mean, they weren't properly understood. I think they should be rehabilitated. Not completely, they should give them the right place in the world.
I see.
But I don't, this is conjectural. I might be talking rubbish, but it's a lot of empirical evidence saying that that these things should happen. So there should be some good derived category, the tame one, it is not the same as the old one. It's not the homotopy category. And even then, there's no Quillen structure, because if there's a Quillen model structure, you will have both left and right calculi of fractions. And this one seems to have only on the right side. So it is, it's good, but it's different. That's my feeling.
Thank you. Thank you, Boris.
Thanks.
Do we have any other questions for the speaker? I mean, I myself was thinking about asking a question about conjecture 6.3 that you just talked about.
Yes.
But so this YE8 paper, does that contain some empirical evidence for this conjecture?
Well, all the stories I told about Wild, and I mean, this is a year ago, I didn't know that there were two of them. I conflated them. I made a mistake. They're different. And they're different. So my error was I was not able to distinguish between two distinct constructions. And they're probably distinct. One of them is good and about which I can say all kinds of things. And the other one is this Wild one, which people have been looking at forever, and it's probably not the same. And so this is about the study of this tame-derived category, inverting subjective quasi-isomorphisms and conjecturing that it's not the same as inverting all quasi-isomorphisms. And presumably a quasi-isomorphism which is not invertible in the tame-derived category. I mean, this is checking under the lamp is this quasi-isomorphism. So the same one that will have a non-zero cotangent complex is probably the same one which will not be invertible when you invert surjective quasi-isomorphism.
Also, you mentioned towards the end that in some papers of Jacob Lurie, there are two notions of cotangent
I believe
complexes.
so, but this is hearsay.
Are they supposed to be equivalent to each other?
No, I think not. As far as I mean, I did look in the 2018 version of SAG, Spectral Algebraic Geometry, but one can read it and pretend to understand, but without understanding anything deep. That's one of the good and bad things about the Lurie writing, right? He writes and you pretend you understand, but you know nothing. So I believe he has a topological cotangent complex and an algebraic cotangent complex. And I think they're really different. And I don't think one is induced from the other. They might be really different. And I think that what I'm talking about should be the algebraic one. But this is all with a lot of
air quotes,
many grains of salt.
Yeah, and as you know, I'm sure Jacob Lurie has a bit of a strange attitude towards publishing.
Well,
so that
I wish I had his anything. Yeah.
Sure.
Yeah.
Okay. Do we have any other questions for Amnon? If not,
I mean, I wish I could get him interested in my stuff, but that hasn't happened yet. So maybe it's a bad sign for me that it's rubbish, but I have a feeling that what I said actually holds water.
Right. Okay, if we don't have any other questions for Amnon, let's thank him again.
Thank you. Thank you for your patience.
And so the video of this talk will be uploaded to the YouTube channel of the series, which was linked in the announcement. If you go back to the announcement, there was a link to the YouTube channel. So I'll upload it either today or tomorrow. Anyway, thank you all for coming. Thank you.
Bye-bye.
Stop recording.
Thank you.